All right, I got a new book for you. Hey, if you got a really tiny binder, you might want to upgrade. You're going to probably have a hard time fitting all this stuff in. Here is a new assignment sheet. All right, so if you turn, I want to say it's page 7. But we're starting a brand new chapter, guys. Great time for you to start over and forget about this chapter. I mean, truly, just start over. A lot of people end up dropping this anyway. It's probably one of the harder tests to put everything together because there's a lot of ways it can go wrong. So just kind of hit reset, start over, and start checking, correcting, and see what happens. I think you'll see, I think you'll be pleasantly surprised. Yeah, start over with the material today. It's the first day, right? Start fresh, start checking and correcting your work, see how that plays out. And again, try something different. So I think we're on page 7. Yes. All right, so we're going to learn a couple things that you probably learned incorrectly in former years. That doesn't mean they were taught incorrectly, but the manner in which you learned stuff probably led you to some certain beliefs. And I find that almost all of my students, when they walk in here and hear this, they're like, whoa, that's not right. So you're going to have to rethink things, okay? And relearn a couple things that are probably not common knowledge to you. Okay, so does anybody know what a root is? I've mentioned this before. A root is a solution, okay? So if I had an equation like y equals x squared, okay, I talk about the term square root. A square root means that the root basically is a double root. Okay, it comes from a math team expression that if I had a certain situation like this and I tried to solve for x, okay, it came from where the actual root value was being squared. Okay, now, when I solved for that, you probably learned, and you probably didn't do problems like x squared equals y. You probably did stuff like x squared equals 25, and then you square rooted both sides. And when you did that, you probably learned that. And I think I've mentioned this before, but the problem with learning this is you learn some bad habits. And the habits are, you start to believe that the square root of x squared is x, which is not. And you start to believe that the square root of 25 is plus or minus 5, which it's not. And most people learn that. But what the reality of this is, I skipped a step. The square root of x squared, because it is a square root and a squared power, basically because it is an even root, and you're going to learn like cube roots, fourth roots and all that kind of stuff. But because it's an even root, when I simplify this, I don't get x. I get, anybody? Absolute value of x. And people are like, what are you talking about? I'll show you more examples in a second. And when I square root of 25, I don't get plus or minus 5. Ask your calculator. Type in square root of 25. It's not telling you plus or minus 5. It's telling you 5. But you've already learned that when you're dealing with absolute value, sometimes it's positive, sometimes it's negative. And you remember doing that back at the beginning of the year? So that would mean that x, sometimes I'm going to get x, a positive value of it, and sometimes I'm going to get a negative value of that x. And when I solve for that and that, I get x equals 5 and x equals negative 5, which means I get x equals plus or minus 5. But it's because of this process. Now, I'm not advising you to unlearn what you've learned, but I can tell you that you're going to get yourself into trouble sometimes. Like, what if this was an inequality? What would you normally do when you solve an inequality? You just bring it down, right? You're not going to change the direction unless you divide them up by negative, and I haven't done that, right? But what would you have done if I got down to this? Would I have said x is greater than or equal to 5, negative x is greater than or equal to 5? Or would I have said x is greater? Do you remember that? And what does greater than mean? Like, I know it's written in the opposite order, but that is bigger than that. Greater means I'd put an or in there, right? Yeah. So if I had an or in there, my answer is not plus or minus, it's, hey, x is either bigger than or equal to the 5, but when I solve here, what ends up happening?
X is
less than or equal to the negative 5 with an or. And bigger than or equal to 5, less than or equal to negative 5 is totally different than bigger than or equal to both. Are you seeing that? And if I got sloppy and skipped this step, and all I did was square root both sides, I would get plus or minus 5, x is bigger than or equal to both of those. That's not what I ended up with, is it? I got x is bigger than that, but smaller than that one. So sometimes you get in trouble when you forget what I put in the parenthesis, in the cloud. And that's why I really want you to know your definition. And that's one of the major topics we're going to talk about today. So all of this in the parentheses right here, it just talks about roots, primary roots, where the square root idea came from. It's nothing really to memorize. But remember, when I'm doing this, I'm getting two values, a positive and a negative, a principal root and a non-principal root. You're not taking the square root of 25 and getting plus or minus 5. These are basically saying there are two answers that would have made this true. And if there's two answers that would have made that true, those are the two square roots. And then also, when I start asking you simple questions like this, what is the square root of 36? I didn't give you an equation. It's just what? It's just 6. So you've got to get away from that mentality. The only reason we have a plus or minus here is because of what? We had an equation that when I square rooted the variable squared, I got an absolute value of x. Are you seeing that? And the absolute value in that equation is what spit out the plus and the minus. Here, you could acknowledge this as, hey, really, this is what I have. The square root of a 6 squared. And you could say, well, based on this, it's the absolute value of 6. Well, what's the absolute value of 6? 6. Now again, if you're looking over here and going, wait a minute, how come the absolute value of x is plus or minus and the absolute value of 6 is not? Again, this is an equation. And if I'm simplifying an equation, aren't there two values right here? I'm going to go back to the equal. Aren't there two values right here that make this true in this equation? Yes, no? Yeah, a negative 5 in there or a positive 5 in there would make that true. There's no equation in here. I'm just simplifying it and I'm calling it a day. And for those of you that are like, for instance, for those of you, I'll get to that later. So let me just talk about these rules and talk about where you have to be careful, and I think you'll be in good shape. So first 3, and then we're going to do lots of different examples. So the properties of radicals I need you to know, starting with this. Okay, and you need to be able to recognize the differences of these. This one has an n. What do you think I mean by that n? Any number, okay? not going to be a 0 and it's not going to be a 1, but it could be a 2, square root, 3, cubed root. Okay? If those two numbers match, but this power is on the outside of a parentheses, okay? So let's just say that was like cubed, or to the 4th power, or to the 5th power, squared. By the way, if it's a square root, I don't bother putting the 2, that's understood. But on all of these, if you see that, what does it look like I'm doing to simplify it? It's just the x. Do I do anything to that x based on that formula? No. No, so if it's positive, leave it positive. If it's negative, leave it negative. No matter what, if that power is on the outside, basically the power and the root, because they match, just cancel each other, and you're left with whatever the number is. Super simple. Because basically, PEMDAS, you would do the outer exponent first, and the exponent's gone, and the radical is gone before you ever have a chance to let it operate. Now, what is the difference between number 1 and number 2? Or number 3? Okay, so that power is now not only just on the inside of the parentheses, but also what?
Under the radical.
Under the radical. Now, if that's the case, this is telling me to not do the radical then the power, essentially, but to do the power then the radical when you're operating on that x. Are you with me on that? Now, in these two cases, whether the number is even or odd makes a huge difference. So if the powers are odd, like 3 and 3, or 5 and 5, or 7 and 7, then the rule works just like it did before. The 3 and the 3 cancel, the 5 and the 5 cancel, 7 and 7 cancels. There's no need for absolute value at all. Just bring the number over. But, this is where people miss it. Only exception to that is this. If it's an even number, and that even number is inside the radical, then you tell me what would have happened to that negative before you ever even got to the radical. It would have become positive because it's an even number, right? So the positive is now gone. And if it's gone, basically that negative 16, that's the need for the absolute value. Because the absolute value says, hey, you don't just copy it over and be done with it. You would have made it positive because of the 4, but before you ever got to the radical. So you'll see all of these, the negative's going to be gone, but it has to do with the absolute value. And on this one, because you don't know what x is, you don't know whether x is positive or negative, you have to show that I know it's going to be positive by putting that absolute value on it. Here, I could write it like that, but I learned back in what grade did you learn absolute value? Tyree, maybe? Maybe before, 7th and 8th grade. You learned what do you do on a number with absolute value? Throw the negative away. Well, why wouldn't I do that? But if I don't know what x is, I don't know whether I should throw it away or not, so I just go, I got to make sure that it ends up being positive. Here, I'm doing the same thing, right? But here I can go an extra step. Now, for those who are like, well, if here you can do that, why can't you do that here? Well, let me show you. If this were true, then shouldn't I be able to plug the exact same number in there and it makes sense? But look, if I plug a negative 25 in for x, is that a true statement? No. It's not. Are you following me? So if you end up with a variable when you're simplifying, and those are both even, and that power is underneath the radical, you've got to remember the absolute value. You technically got to remember the absolute value here, but you can just simplify it and make it positive. Y'all seeing this? Okay, if you're not, you're going to catch your errors tonight or today, and hopefully you'll start minimizing stuff. So let's just walk through some of these. Right here, 4th root of 3, all of it raised to the 4th. Now, if the 4 is on the outside, do I have to worry about any absolute value? No, this 4 and that 4th root are going to cancel, leaving me just a 3. What about this? 5 on the outside of a 5th root. Do I have to make this absolute value? No, because that 5 is on the outside and it's odd. In either one of those, I would not have to do absolute value. That cancels. What about this? I don't need absolute value though, do I? Because that 4 is on the outside. There's not parentheses, but it is on the outside of the square root. So that 4 would have canceled out that 4th root before I ever got to the happy face. I'm good. What about this? Can I make that fit my agenda? Yeah, because 243, because I wanted to do a powers quiz today, but be ready tomorrow for a powers quiz.
Very good.
All right. What can I rewrite that as? 3 to the 5th. So I have the 5th root of 3 to the 5th. Now the 5's underneath. Do I need absolute value? No, because it's odd, right? So that 5 and that root would cancel, leaving me a regular 3. What about this? I can just cancel them because they're odd. Even though it's underneath, it's odd. Odd doesn't use absolute value. -2. What about this? Do I need absolute value? No, because it's odd. Even though it's underneath, it's odd. What about number 7? Can I make that fit my agenda?
Yes, 3 to the 4th.
That's 3 to the 4th, so the 4th root of 3 to the 4th. Now technically, because that 4 is underneath and it's even, these cancel and I get absolute value of 3, but we know that absolute value of 3 is what? 3. What about this? Because it's even and that 6 is underneath, even though they cancel, technically absolute value of -2, which is 2. Right? And here, because it's an even number and it's underneath, 4th root 4, those 4's will cancel, but what?
We don't know what it is.
I don't know whether happy face is positive or negative, but I have to ensure that it's positive. So I have to put an absolute value on it and leave that absolute value in case it's negative, so future generations will know to make it positive. Y'all seeing this? Okay, let's ugly it up a little bit. What if I'm solving equations with it, which we already have done one of these already? I've already mentioned this, so I'm just going to walk you through it again. To solve an equation like this, I guess you could move the 49 over and then factor it and solve, but that's not going to help you if 49 was 48. That wouldn't be a difference of 2 squares. So what I'm saying is if it is a perfect square, you could subtract it and then factor it, but if it's not, the method I'm showing you is probably better. So we're going to square root both sides. And what's the square root of the x squared? Technically it's what? Absolute value. And the square root of 49 is, based on my rule, technically absolute value of 7. But absolute value of 7 will simplify by not absolute value of x. So how would I solve that? Sometimes x is positive 7. Sometimes sometimes negative x is 7. And when I solve, plus or minus 7. But I have no problem with you just doing this. Square rooting both sides, skipping all of that, and writing x equals plus or minus 7. But if it's an inequality, I'd be careful and write out some steps. What if it's a little uglier like this?
Add 7 divided by 2.
So when you add 7, you get 32. When you divide by 2, you get 16. So that would give me, if I add 7 to both sides, and I divide by 2, at this point, what can you do? That's right. So technically, it's absolute value of x equals 4. But when I solve it, I end up getting x equals plus or minus 4.
Why would you just not write, or well, actually, never mind, this is too much.
Go ahead and ask it anyway.
Why would you not just write x equals the absolute value of 4?
Because that's not true, but
Yeah,
you could write that,
okay,
but then you wouldn't be finished.
okay, because you can still.
Because you can still go further, right? And technically it's that, but that simplifies to a positive 4. This, I just don't know if it's negative, so I have to ensure that it stays that way and then break it up and find those values. All right? Now, what if these numbers don't match? Like, what if it's 3 and 12 or 3 and negative 6? So to cube them, if I really want to be sticklers about this, I have to rewrite it in one of my forms. So if I'm cube rooting something, I would need to be cube rooting a cube to be able to simplify. So what am I cubing here that would give me 10 to the 12th? Do y'all see what he just said? He said 10 to the 4th. Do you see that there is a 10 to the 4th that I am cubing? Y'all see that? Well, now I can use my rule. Because we know that a power to a power would multiply and give me 12. Are y'all seeing that? Now I'll show you another way to think about it. But technically, my rule says if you can make it fit my rule, then you're okay. Now what's the rule on a cube root of something cubed? Do you need absolute value? So all I would have was what? That would cancel, and it would give me 10 to the fourth, which we know is a 1 with 4 zeros. Now another way to think about it is like, well, I've got 12 tens under there. I don't encourage you to write this, but you could visualize this. 5, 6, 7, 8, 9, 10, 11, 12. And for every 10 cubed, what's the cube root of 10 cubed? A 10? Well, how many 10 cubes do you have in there?
4.
So you would have 4 tens that I could pull out of this radical and put on the outside, and you'd have nothing left over. Does that make any sense? So you could look at it as 10 to the 12th is just 10 cubed, 10 cubed, 10, or heck, it'd be better than writing this. You could say 10 cubed, 10 cubed, 10 cubed, 10 cubed. But it makes more sense for me to just do that. Sorry. Not that. Yeah, 10 cubed, 10 cubed. You could do that if you want and say, what's the cube root of 10 cubed? Pull a 10 out. What's the cube root of 10 cubed? Pull another 10 out. Cube root of that 10 cubed? Pull another 10 out. Cube root of that cubed? Pull another 10 out, and there's your 10 to the fourth. Right? But if you can just rewrite it using your rules, I think you're going to find a little more luck here. What about this thing? Can you see what you're cubing here? Do y'all see that? Now, if you don't like the negative exponent, then get rid of the negative exponent. 1 over 10 to the 6th. So if you don't like it. But if you can look at this and say, wait, that's a 10 to the negative 2 cubed. That is. Well, I'm cube rooting them. So what is the rule? The cubed and the cube root would cancel. There's no absolute value because it's odd. And all the odd ones are no absolute value. And you would just take the 10 to the negative 2 and simplify it. 1 over 100. If you thought about it this way, I guess you would say, all right, we have the cube root of 1 over 10 squared, all of that to the third. And if you do that, the 3's cancel, leave you with 1 over 10 squared, which is, again, 1 over 100. What about number 13? How could you think about this? So you said x to the fourth cubed? You tracking with me? Do I need absolute value on this? Why not? Because there's odd, so those would just cancel and leave me x to the fourth. What about 14?
X to the third.
So you would think about this as x cubed to the fourth? Are you with me on that? I'm making it fit my narrative. Do I need absolute value on this? Yes, good. And then 15? X to the 6th to the 4th? 4 through to that? Do I need absolute value on this guy?
Yes.
Tell me why, Lily. Check it out. Now, if you did this, it'd be really hard for me to count off any more than like a smidgen. Not even a dot, 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 like a half a point. But really, we always want to simplify completely. And although you're saying correctly, that's the rule. The fact that I'm going to raise it to the 6th power is going to make it positive anyway, isn't it? Right? It's because it's an even power. This here was an odd power. So that's not going to get rid of the negative. But even if it was negative, the 6 is going to make it positive. So wouldn't that be a little bit more simple? So, but if you, I'll leave the absolute value up there just because these happen to be the same. All right, when it's even, it happens to be even. All right, let's keep plugging along. What about this? Are y'all aware? This is something that people really mess up every year. Are you aware that if I have a radical with two numbers being multiplied or divided, only multiplication or division, that I can square root or cube root or whatever root it is, each part, and then multiply it? So for instance, you've probably done this a million times, but if I have something like root 12, you probably look at this and go, oh, that's 2 root 3. Are y'all with me on that? If you're not, the reason why that works is because 12 is 4 times 3, I can think about this as a root 4 and a root 3. And then I can square root the stuff I can square root, leave the stuff I can't alone still in the radical. So this would become a 2 times root 3. That's what this is saying. So why did they say if it's real numbers?
Because sometimes it's a negative or something.
Yeah, think about this. What if this was something like a square root of negative 12? If this is a square root of negative 12, and I were to change this to negative 4 times 3, or root negative 4, I'm not allowed to square root of negative 4. I'm not. And just ignore the negative. The negative means something. And you probably learned that it means a what? It means there's an I in there. Because as you'll learn in a second, the square root of a negative 1 is an I. Now what you need to remember is that's a square root of a negative 1. We will not have cube roots or fourth roots or fifth roots that give me I's. They don't. Only square roots do. So that's the only time. If I see a cube root of a negative or a fifth root of a negative, I can do that. I just pull the negative out. But square roots of negatives give me I. So you got to be careful. I use this dumb saying that I say, when you're square rooting stuff, take your eyes out so you can see more clearly. So when you are square rooting things like this, the temptation, like if I was multiplying those two, is to go, oh, if you're multiplying those two, according to this, to multiply them, you just multiply the numbers. But if I multiplied those together, I would just get root 36, wouldn't I? And you would think that this was equal to 6, but it's not. But if you take your eyes out, like right here, that's why they have to be real. If I take the I out, because the square root of the negative number is an I, the square root of the negative number is an I, take those I's out, and you end up getting an I squared on the outside, and you probably have already learned that I squared is negative 1, and that ends up negating this. So remember that saying, I'll mention it somewhere in these notes, that if you have a negative in a square root, basically you're taking it out. You're not really taking it out. You're thinking about it like the square root of negative 12. You're thinking about it like this, is square root of negative 1 times square root of 4 times square root of 3. And the square root of the negative 1 would be the I part. And then the square root of 4 and the square root of 3, you could actually simplify. But you are still going to have that I in there somewhere. So we'll talk about that more and more and more as we go through there, but just be aware of that. But that's why it says are real numbers. You've got to pull that negative out or it's going to deceive you over and over again. Right? So take your eyes out first so you can
See clearly.
see more clearly. All right, so check it out. Let's look at a couple of these and we're going to try to make them fit my narrative again. Now based on this, it goes two ways, right? I can break up a square root or I can multiply them back together. I can break up a radical or I can combine them into one radical. Our equation means it works both ways. So right here, how would I multiply this together? You think your best plan is to go 12 times 45? I don't need it. That's going to give you 540, and now you're going to like, what am I doing with the 540? So it's already partially broken up. What would be an even better idea?
Break it up.
Break it up even further? How can I break up that root 12?
2 or 3.
So root 4, root 3, which is going to give me a 2 root 3. How do I break up that root 45? Which is a root 9, root 5. Are you with me? So now I can simplify that into a 2, that into a 3, and the root 3 and the root 5. I can't really do anything with that, so I'm going to pull all that together into one radical and call it a root 15, and I get 6 root 15. Y'all seeing this? You see any addition going on here? No, this is only rules for multiplying and dividing. What about this one right here? I got cube roots.
So the first one would be x times root x.
Okay, so what you're saying is break that up into a cube root of an x cubed and a cube root of an x.
Correct. And then the second one would be x squared. Right?
Cubed. You're saying to do this?
Yes. And then
Are y'all tracking with me right here? Another option would be to go cube root of x cubed times cube root of x cubed. Are y'all seeing this so far? There's 4 of them there, so I'm putting 3 of them, 1 of them, but I'm breaking it up so that this I can simplify easily. Here, I'm changing x to the 6th to x squared to the 3rd, so I can use my rule and simplify that pretty easily. But this, I'm not going to be able to do much with, am I? So when I put it all together, I've got x cubed times the cube root of x. I don't know that I would have done this, honestly. What I would have probably done is a little different. I might have looked at this and said, you know what, there's 10 x's under one radical. And how many x cubes are in x to the 10th? 3 with 1 left over? Are y'all seeing that? So if I looked at it like this and said, wait, this is the same thing as 3x cubes with another single x left over. To me, that's a little easier because it's still all 10 of them. And I can say, all right, this 3 and that 3 would cancel, leaving me an x cubed coming out, but I still have a cube root of x left over. You just got to get comfortable with what you like and kind of feel good about. What about 18?
Maybe pull out a 2 root 6 out of the 24.
Now, that's what a lot of people do, and there's nothing wrong with that. So what he's, and then I'm going to show you something else. Right here, that right there is 4 times 6. Are you with me? 4 times 6. So if I'm visualizing that 4 times 6 right there, I can take the square root of the 4, which is 2, pull the 2 out with the 5, and now I have 10 root 6. I could do that. I could look at this 3 root 8, and I could think of it as, well, there's a 4 in that 8, so 4 times 2, and I could take the square root of that 4, which is 2, bring it out, and I get 6. But then what do I have left? If I multiply this together, that gives me 60 root 12. But now there's more to take out, isn't there? So before you just start pulling out little bitty things all at once, sometimes it's good to think about the fact that, remember, 5 times 3 is 15, but this root 24 and root 8 could go all together under one radical. All right? And if I did that, it might be really easy to think of the 24 as a 3 times 8, and I've already got that other 8. And now I can see what I can take the square root of, right? If there's 2 8s under there, which is 64, what's the square root of that 64? So pull an 8 out and multiply 8 times that 15, and then all you'd have left is the root 3. So whatever that gives me, 120 root 3. How about this 19? Now on that negative, people are always tempted to take the I out. But what did we say the definition of an I was? The square root of negative 1. If you see an I anywhere else on an odd root, guess what you do with it? You just change it to plus there, pull out a negative 1 or a negative. Do that. If it's a square root of a negative, take an I out. Now, how do I simplify cube root of 8 times cube root of 8 now that they're both real, or now that they're both positive numbers?
Wait, if it said negative 8 squared, you would pull an I out? Is that what you're saying?
No, if that's a cube root with a 3. If it was like a square root of 8, because it's a square root, I would have to take an I out. But if it's any other odd power, and you're not going to see other even powers like 4. You're not going to see a 4th root of a negative 1 in this class. But the answer is it's the square root of a negative 1, but you're not going to see it in this class, pre-cal, anywhere in college or in high school. So if it's a 2 right there, which is the square root, take an I out. If it's any other number, 3, 5, 7, 9, 12, whatever else, 11, any other odd number, just pull a negative out and be done with it. Now what's the cube root of 8? Cube root of 8? 2 and 2 is 4. Don't forget the negative. What about this thing?
Same thing.
Same thing about the negative, right? So make it positive and pull a negative out.
Then,
And I'm dealing with cube roots.
2
Root times 4.
oh,
So 16 and 16 is what? A bunch of 2s?
2, 1.
So you basically have 8 2s in there,
4.
right? So how can I rewrite that so that I can, or how would you think, what can I take out of here? I would need how many 2s underneath to take 1 out?
3 2s to take 1 out.
3 of them underneath there, right? So maybe I could rewrite this as 2 cubed with an extra 2 left over. Does that make sense? And when I'm taking a cube root of the first 2 cubed, a 2 comes out. A cube root of the next 2 cubed, a 2 comes out. And the last one's 2 squared. I don't have enough, so I'm going to leave that as the cube root of 4. So -4 cube root of 4. Could I have done that a different way? Yeah. I could have looked at 16 and 16 as 4 squared and 4 squared. Or 4 to the 4th. If I did that, how would I have looked at this? There's a 4 cubed, and just what else? One other 4. So I could take a cube root of 4 cubed, pull a 4 out, and a cube root of 4 left over. Y'all seeing this? Y'all remember rationalizing denominators? Okay, I'm going to throw some curveballs at you in a second. So, unfortunately, this bell's going to ring in a second. But let me just point out something really quickly, and then you're going to do the best you can tonight. And we're going to pick up with this because there's a chance I can't. Let me see how far I wanted to go. Oh no, we actually are almost done. Okay, be careful. A lot of people, when they rationalize denominators, they do this. They just think it's magic, and they go, oh, 3 root 2 over 2. But what really happened here?
Multiplied.
I really got root 4, didn't I? And the root 4 just happened to be 2. So that's why I simplified. But let me ask you a question. This is a cube root, not a square root like over here. So if all I do here is go cube root of 2, cube root of 2, and I go 4 cube roots of 2 over 2, where did I go wrong? Well, I went wrong because I really didn't get 2. I got what? And the cube root of 4 is not 2, is it? So what did I really need to do on this cube root? I didn't need to make sure that I had 2 2's in there. I needed to make sure that I had 3 2's in there. And I only started with 1, so what did I really need to do?
Multiply by root 4.
Multiply by the cube root of 4, and make sure you're writing cube roots on that. So that would have given me 4 cube roots of 4 on the top, and then what on the bottom? Cube root of 8, which does simplify to a 2. Which actually simplifies even further after that, doesn't it? So over here, if I have a cube root of 25, how do I rationalize it? What do I need here?
Times cube root of 5.
I already have 2 5's, right? So how many total 5's do I need on a cube root? 1. So I need 1 more there. Now you could also put 2 25's, 25, 25, so you'd have 3 25's, but then you're going to have to simplify a lot at the end. So think about this already as 5 times 5, and a cube root, I need 3 of them. So an extra 5 on the top, an extra cube root of 5 on the top, extra cube root of 5 on the bottom. 4 cube root of 5 over what? Cube root of 125, which is 5. And then lastly, what about this 4th root? What do you think that means? Obviously, 4th root, I would need how many 2's on the bottom?
1.
Well, how many do I need in the end? 4. How many do I currently have? 3. So I need 1 more 4th root of 2 to give me the 4 2's I need. Yeah, does that make sense? I need 4 2's, 2 to the 4th, so that the 4th root of 2 to the 4th will simplify. And check it out. 4th root of 2 to the 4th, there's my 2. All right, do the best you can, and we'll see you guys tomorrow.